Let's take this contingency table, and as you can see, the rows are going to be friends' drug use, and the columns are going to be the respondents' drug use. So they're both dichotomous, yes or no, and yes or no, and we're measuring is if your friends use drugs, are you going to use drugs? Okay, so ask yourself the question to begin with: how many cells are in this contingency table? It's a 2 by 2. See, 2 by 2. Everything else is a descriptor. So 75, 25, 15, and 55 are the actual cells. So let's get started. Let's take a look at what we could do with this. Okay, and as you could see, we are going to say your friends, if your friends use drugs, yes, chances are you could see already that you're going to use drugs. Your chance of using drugs is higher. If your friends use drugs, no, okay, your chance of using drugs is lower. Okay, so let's pop over. And how do we analyze this? Number one, we state the null and alternative hypotheses. The null hypothesis is there is no relationship between a friend's drug use and drug use habits and the respondent's drug use habits. The alternative hypothesis is, of course, that there is a relationship between friend's drug use and respondent's drug use. Here's the table. So step 2 says that we have to compute the sum for each row and column. All right, so let's go ahead and do that. And as you can see, the total here is 100, 75, and 25, and the total here is 70, and the total for the columns is 90 and 80. So 25 and 55 make 80, and 75 and 15 make 90. Okay, let's pop over. Step 3, compute the expected frequencies, the row total times the column total divided by the total number of observations. Okay, so here we are, and we are going to take the row total and we're going to compute the expecteds. Okay, so let's just pop over, and you can see that the observed frequencies are 75, 25, 15, and 55. What are the expecteds? Okay, the expected for that first cell is 100 times 90, row total times the column total, divided by 75, which is the total number of observations, gives us 52.95. Okay, and that step 4 is apply the formula and compute the chi-square statistic. So remember, chi-square equals the sum times the observed frequencies minus the expected frequencies squared to get rid of the sign, divided by the expected frequencies. Okay, so 4a, compute the difference between the observed and the expected. There you go. So it's observed minus the expected is 22.06, etc., etc., etc. And step 4b is compute the squared differences. So we can just go ahead and square those guys up. 22.06 times 22.06. There you go for each cell. And 4c is we take those squared differences and divide them by the expected value, which we've already computed, and there's what we're getting: 9.19, 10.34, 13.13, and 14.77. Step 4d is sum up across the cells, and there we go. And there's the chi-square statistic. Step 5 is determine how many degrees of freedom there are, because don't forget we have to go and look at that critical region. So remember, the degrees of freedom equals the number of rows minus 1 times the number of columns minus 1. So it's a 2 by 2 table, so 2 minus 1 times 2 minus 1 equals 1 times 1 equals 1. That's the degree of freedom, 1. And step 6 is check the chi-square distribution table. So for chi-square equals 47.43 with a degree of freedom equal to 1, is the association between friends' drug use habits and respondents' drug use habits significant? Okay, the individual's drug use habits varies according to the friend's drug use habits, and this difference is substantial enough not to be attributed to chance. Step 7, let's interpret the results. All right, here we go. Let's say that there is a significant association between friends' drug use habits and respondents' drug use habits. Chi-square equals 47.43. The degree of freedom equals 1 with a p less than 0.05. All right, then report some percentages. Let's interpret the results. Tell me, what are the key results observed in the table, and what are the possible explanations for these results? Do you want to respond to that in the on the discussion board? Go ahead. Okay, let's do a quick review of chi-square. What's it for? It's to measure associations between nominal and ordinal variables. The null and the alternative hypothesis. What's a null hypothesis? You remember? It means that there's no significant association between the two variables. What's the alternative hypothesis? Go ahead, tell me. That's right. It means that there is a significant association between the two variables. Okay, in chi-square you compare observed frequencies with expected frequencies. Okay, what are observed frequencies? Do you remember? They're the ones that you observe in your sample. What are expected frequencies? Go ahead, just blurt it out. They are the estimated frequencies that you would observe if there was no relationship between your variables, such as if the null hypothesis was true. Example using this class. Let's say that gender, male or female, and punctuality, homework late or not late. Okay, the expected cell frequencies equals the row total times the column total divided by n. Remember, that's a pretty easy one. So let's do another example. Smoking, no and yes. Drinking. So how many cells in this contingency table? Could you tell me? Yes, that's right. It's a 2 by 2 table. There are 4 cells. And so if you smoke, are you going to drink? What is this table telling us? If we smoke, yes, chances are we're going to not necessarily drink more. So that's interesting. Here's a 3 by 3 table. So why is this a 3 by 3? Because we have low, average, and high, none, some, and lots. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Because it's 3 by 3, or 3 times 3, it's 9. Okay, here's the chi-square formula. You remember? Chi-square, here's the formula, you remember it, and it says the difference between what is observed in the data and what would be observed in if the null hypothesis was true. And why do we divide by the expected frequency? The number of categories and degrees of freedom. With chi-square, you add values for each category. So the more categories, the larger the chi-square value is going to be. Remember? Degrees of freedom are used to take this into account. Remember? Degrees of freedom equals the number of rows minus 1 times the number of columns minus 1. Here are the conditions for using the chi-square test. You have to have 2 nominal or ordinal variables, random sample. They have to be mutually exclusive categories, smoke and drink, male and female, homework, late, not late. Get it? Mutually exclusive. Expected frequencies must all be greater than 1, and no more than 20% of the cases in the contingency table should have an expected frequency of less than 5. New stuff alert. Okay, this is measuring the strength of association between 2 nominal or ordinal variables. Remember that the chi-square test is not a measure of the strength of the association between 2 variables. It simply tells us whether there is a significant relationship between the variables. If your chi-square statistic is not significant, that means that your variables are independent from one another, and there's no point in reporting the strength of the association. If your chi-square statistic is significant, you need to measure the strength of the relationship. And these are the most commonly used measures of strength. And SPSS will do these for you, so not to worry. The first one is phi. The second one is Kramer's V. The third one is gamma. The fourth one is Kendall's tau B. And the fifth one is Kendall's tau C. Okay, let's just talk really quickly about phi. It is used between two nominal variables. Okay, phi equals the square root of chi-squared divided by n. And it's used to measure the strength of association between variables in a 2x2 table. Okay, that is two dichotomous variables. All right, phi is symmetrical. That is, it does not make the distinction between the independent variable and the dependent variable. The phi value is always going to be between 0 and 1. And the higher the phi value, the stronger the association between the two variables. And that's the thing to remember right there. Okay, Kramer's V between two categorical variables with tables larger than 2x2, Kramer's V is equal to the square root of chi-squared divided by n times k minus 1, where k is the smaller number of either rows or columns. Don't worry about this. I'm just giving you the formulas so that you'll know them. SPSS is going to do this for you. Remember, Kramer's V serves the same purpose as phi, but it's used for tables larger than 2x2. What do we use phi for? Tables that are 2x2. Okay? Kramer's V is also symmetrical. That is, it does not make the distinction between the independent variable and the dependent variable. The V value is always between 0 and 1, just like phi, and the higher the V value, the stronger the association between the two variables. The next one is gamma. We use this between two ordinal variables. Okay, so gamma, this is the symbol for gamma, equals NC minus ND and divided by NC plus ND. And NC equals the number of concordant pairs, and ND is the number of discordant pairs. Don't worry about this too much. You're not going to need to know this. SPSS is going to do this for you. Here are some examples of concordant and discordant pairs. You could put this on pause and read it. I'm going to go on. Remember that gamma is for two ordinal variables, and it's used to measure the strength of association between variables in a squared contingency table. It's got to be 2x2, 3x3, 4x4, 5x5, etc. All right. Gamma is also used, is also symmetrical, and it doesn't make the distinction between IV and DV, and the gamma value is always between -1 and 1, unlike phi and Kramer's V. When there is no association between the variables, gamma is going to equal 0. And the higher the y value, the stronger the association between two variables. And I'm going to skip over to the next video now. See you in a minute.